Alright, so today we're going to have a look at other induction proofs. So far we've only looked at induction proofs that prove things are true for all positive integers or all even integers, and we've done it algebraically in a way that we've proven true for n equals 1, assumed true for n is k, and then proven true for n is k plus 1. Now, we've done that algebraically. What I mean by that is we've had a sequence of numbers that has been added together, and then we've used some formulas to figure out a relationship between k and k plus 1. While we're going to always follow that process, we don't have to do it algebraically, so induction can be used to prove things in geometry and in calculus as well. So we're going to start with a calculus example. So we will start by looking at using induction to prove calculus results. Important to know that although these results are actually true for all real n, induction in this case only proves that they are true for all positive integers. Now, if you go into uni and do further mathematics, you'll learn the difference between induction, which is this type, and then strong or hard induction, which proves true for all integers, and we can do it for negative values as well. I think it's either called strong or hard induction. I'm not quite sure what it's actually called. So example number 1, we're going to prove that for any positive integer n, d by dx of x to the n is equal to n x to the n minus 1. Again, our first case is going to prove true for n is 1. So d by dx of x to the power of 1, we know is going to be just 1. And then 1 times by x to the 1 minus 1, well 1 minus 1 is 0 and x to the power of 0 is 1, so it's 1. Therefore true for n is 1. Our next step, of course, with induction is to assume true for n is k. So we're going to assume that d by dx of x to the power of k is equal to k x to the k minus 1. That's our assumption there. Next, we're going to prove true for n is k plus 1. So as we can see, it's the same process, but this time we haven't actually gotten a sequence of numbers added together. We've got some sort of calculus result, but we can still apply the same process. So we're going to try and attempt to find d by dx of x to the k plus 1, and we're required to prove that it's equal to k plus 1, x to the k plus 1 minus 1, which is x to the k. Now, d by dx of x to the k plus 1, well, we could split that into x times x to the k using our law of indices. And then we could apply the product rule. The product rule says that we differentiate the first thing and times it by the second thing. And then we differentiate the second thing and times it by the first thing. Now, importantly, we can't just take the differentiation of this using our rule because we're assuming we don't know how to use that rule for this particular indice here. We're required to prove this, so we can't actually use it. All we can use is our assumption, and in this case we're also going to use our base case. That's something we also haven't seen before, where our base case, n is 1, is going to be important in our solution. Don't know why that's so blurry down there. So d by dx of x, we already know is 1, and that's from our base case. And we know from our assumption that this is equal to k x to the k minus 1. That's from our assumption. Okay, so we can say, well, first of all, d by dx of x is 1 times by x to the k plus, we've just said d by dx of x to the k is k x to the k minus 1 times x. So using our law of indices for the second thing, but first up for the first thing, that's x to the k, plus we can combine these two, k minus 1 plus 1 is x to the k. Factorising out an x to the k, we're left with k plus 1 x to the k, which is what we're required to prove, QED. Therefore, true by induction. All right, let's go on to the next one. Okay, now we're going to have a look at a probability example. Now again, just because I'm a bit sick of writing, I'm just going to start with the n is equal to k term. So we're going to assume that x plus a to the k is equal to the sum from r is 0 to k of k choose r times x to the k minus r times a to the r. And we're now going to prove that it's true for n is k plus 1. So we're required to prove, we might just write this in red, we're required to prove we're going to try and end towards x plus a to the power of k plus 1 is equal to the sum from r is 0 to k plus 1 of k plus 1 choose r times x to the k minus r plus 1 times a to the r. If we look at the left-hand side of this expression, x plus a to the k plus 1, that's actually equal to x plus a times by x plus a to the k. Now from our assumption, we know that that is equal to the sum from r is 0 to k of k choose r, x to the k minus r, a to the r. Now we can just expand that, that's just like a constant or one expression outside of it. Now we can put first all this x into here, so it's going to be equal to the sum from r is 0 to k of k choose r times x to the k minus r plus 1. So we've expanded this x to here and plussed it up to here. Now we're going to expand out the a plus the sum from r is equal to 0 to k of k choose r, and I've actually forgotten an a to the power of r over here, of x to the k minus r. Now we're going to expand out this a and put it up here, r plus 1. Okay. Our next step is we want to try and combine these two sigmas. And there's a bit of a problem here because we've got quite a number of things that are different. Specifically, we've got an r plus 1 here and an r here. So let's try and get rid of that. Let's say that this is equal to, we're going to leave this the same, r is 0 to k of kr times x to the k minus r plus 1 times a to the r. We're going to take out 1a, and the way we're going to do that is by moving everything in this sequence across from by 1. So instead of starting from r is 0, we're going to start from r is 1. And if we move this whole sequence up by 1, instead of ending at k, we're going to end at k plus 1. So if we just move that sequence over by 1, it's the same thing. We're like picking it up and putting it over by 1. So this will be k. Now r is going to be r minus 1. We moved it across by 1. So to go from 1 back to 0, where r, we're going to take away 1 from r to go back to where you started. So the new starting point, or the new end point, the new starting point is now r minus 1. And that's because our k hasn't actually changed in value. If we move everything across by 1, we know that in a combinatorics, the thing on the bottom of your combinatorics can't be larger than k. So if we move everything across by k, then the thing on the bottom can't be larger than k. So we're going to take off 1 from r to accommodate for that. Because if we didn't do that, the last term would be r plus 1, which would mean it would be bigger than k, and that wouldn't work. Or we would have k plus 1 as our last term, which wouldn't work, and we can't do that. Okay, so if we do that, we've got x to the power of k minus r. We've moved it all by 1, plus 1. Now our last term, it's not going to be r plus 1 anymore. We're taking away from it r minus 1. So r minus 1 plus 1 is a to the power of r. So that becomes that there. So again, our last term, we've moved it across by 1, so it becomes that now. Okay, now the last term in this expression is going to be in this expression here. We're almost ready to combine these because this is the same and that's the same, and that's the same and that's the same, but this is now different here, and the other thing that's different is these sums. So what we might do instead is we might take out the last term of this. So we're going to leave this first thing as the same. We're going to leave this the same, and we might take out the first term of this one and the last term of this one. So if we take out the first term of this one, the first term of this is going to be x to the power of k plus 1. If we put a 0 here, it's going to be x to the power of k plus 1, and everything else is going to be 0. K choose 0 is 0, we put a 0 here and a 0 here. So the first term is that there, plus, now if we take out the first term, it's now going to be r is 1 to k of k choose r times x to the k minus r plus 1, a to the r, plus, we don't want a k plus 1 here, so we're going to take out the very last term. The last term is this is going to die because k minus k plus 1 is 0, so that dies, and it's going to be r is k plus 1. So the last term, first of all we've got the sum from r is 1 to now k, we're taking out the last term, k r minus 1, x to the k minus r plus 1, a to the r, plus the last term, a to the r plus 1. Now we can combine these sigmas. So we've got x to the k plus 1 plus a to the r plus 1 plus the sum from r is equal to 1 to k of x to the k minus r plus 1 times a to the r outside of k choose r plus k choose k minus 1. But we know that k choose r plus k choose r minus 1 is equal to k plus 1 choose r. So this, we've got x to the k plus 1 plus a to the r plus 1 plus the sum from r is 1 to k of k plus 1 choose r times by x to the k minus r plus 1 times a to the r. However, this whole expression here, this would be still the first term, and this would be the last term. So what we can do is say that actually should be a k plus 1 up there. That should be a k plus 1, k plus 1, k plus 1. So this is the first term, and this is the last term. So we can make the first term a 0 and the last term will plus 1, and we can put it under one big summation. R is 0 to k plus 1 choose r, x to the k minus r plus 1, a to the r. Done. That was very tricky. That's probably hopefully as hard as induction can get, those probability ones. In saying that, let's change it all completely, flip it all on its head and do something called induction in geometry, or deductive proofs involving geometry and induction. So we've got to prove that the sum of the exterior angles of an n-sided polygon is 360 degrees. Okay, so again, we might want to just prove, say, for n is equal to, n is 3 would be the minimum. So let's have a look at that. Let's do a triangle. And let's say it's an equilateral triangle. Well, by supplementary angles, this is 120, this is 120, and this is 120. So therefore, 360 degrees is the exterior angles of that triangle there. Let's assume true for n is k. So let's assume that a k-sided polygon has exterior angles adding to 360 degrees. Now let's prove true for n is k plus 1. Let's draw a k-sided polygon. 2, 3. So we might say that this is our k-sided polygon. And we want to add a k plus 1th side. So we might go like this and this. And that's going to be our k plus 1 sides. So we might call this A, B, C, and I might extend my exterior angles out like this. What I might extend this out to here, and extend this side out to here to point E, D, and F. Okay. So let's think about, we know that the k-sided, we've assumed that the k-sided polygon has an exterior angles of 360 degrees. Now, the exterior angle of this new polygon is going to be the exterior angle of k-sided polygon. And then a few things are going to happen. We're going to minus angle. We're going to get this angle here, and we're going to take away this angle here. So we're going to get CAB, and we're going to minus CAB from the exterior angle DAB. So we're getting this angle and we're taking it off that angle there, because this is our new exterior angle here, no longer is it this. We're also going to minus angle CBA from the exterior angle EBA. So we're minusing CBA from this whole exterior angle EBA, and we're getting the new exterior angle EBC. We're also, though, going to plus our new exterior angle of ACF. ACF. So therefore the sum of the exterior angles of our k plus 1-sided polygon is 360 minus CAB minus CBA plus our new angle of ACF. However, we also know that ACF is equal to angle CAB plus angle CBA. So ACF is equal to that angle, that plus that angle, by the exterior angle of a triangle rule. So we can replace this with ACF. So this is equal to 360 minus ACF plus ACF, which is equal to 360. So therefore, the exterior angles of our k plus 1 polygon is 360 degrees. Okay,